is washing your hands with soap so effective? It may seem like a simple question, but it has quite a complex answer that requires us to consider how molecules interact in liquids. Esto es Real Chem. One of the things I love about chemistry is that it helps us explain the world around us. But even more, I love how chemistry is fundamental in helping us keep people safe and protect the environment. This topic is a great example. Exploremos. Let's learn the meaning behind two words, miscible and immiscible. You can mix any amount of water with any amount of ethanol, and you will get a nice homogeneous mixture. This means water and ethanol are miscible. But if you mix water with oil, like in a salad dressing, they don't mix. You can shake it up, but eventually the oil will separate into its own layer. We say that water and oil are immiscible. Why does this happen though? What is the difference between oil and ethanol that we get such different behaviors? Well, it is mostly related to something chemists call polarity. Water and ethanol are both polar molecules, so they have similar intermolecular interactions, such as dipole-dipole forces and hydrogen bonds. Oil, on the other hand, is nonpolar, like octane and hexane, which are different types of oil. Nonpolar molecules tend to be miscible in each other because their intermolecular interactions are similar. They arise primarily from dispersion interactions, like dissolves like. Polar and nonpolar compounds, however, tend to be immiscible because their intermolecular interactions are so different. We can view water and oil as being two ends of a spectrum. Ethanol lies on the water-loving side. We say it's hydrophilic, from the Greek hydro for water and philic for loving. Hexane lies on the oil-loving side. We say it is hydrophobic, phobic meaning fear, or water-fearing. The experiment we use to locate molecules on this spectrum is pretty intuitive. We add the compound to a mixture of oil and water and measure how it partitions between these layers. If the molecule resides primarily in the water layer, it is hydrophilic. If it resides on the oil layer, it is hydrophobic. We can get more quantitative by introducing P, the ratio of the concentration in oil to than in water. If the ratio of P is less than 1, the concentration is larger in water than in oil. And that means the molecules prefer water. It is hydrophilic. If the ratio is greater than 1, the molecule prefers oil, and it is hydrophobic. Because the ratio spans a large range, we use a mathematical trick, and we take its logarithm. If the logarithm of P is less than 0, it is hydrophilic. And if the logarithm of P is greater than 0, it is hydrophobic. For example, ethanol's log P is minus 0.18. For hexane, log P is 3.9. The Wikipedia page for many molecules includes the value of log P. This is because it tells us a lot about the molecule and its behavior. For instance, in our bodies, hydrophobic molecules such as vitamin A end up in our fat, and so stay in our bodies for a long time. We have to be careful not to take too much vitamin A. Vitamin C is hydrophilic. It stays out of our fat and is easily excreted in urine. So it is safe to take larger doses of vitamin C. The fate of molecules in the environment are also related to log P. Pollutants that are hydrophobic will tend to end up in the soil, while hydrophilic pollutants tend to end up in streams and rivers. And this is where soap comes in. Soap contains molecules with a hydrophobic head and a hydrophilic tail. These molecules surround hydrophobic molecules like oil with their tail pointing in and their head pointing out. This makes the entire unit hydrophilic, so it can be washed away with water. Bastante cool, no? So explore and remember to have fun.